Quantum field theory states that the universe is made of quantum fields,
and that each of these fields have a fundamental particle associated with it. To help with these particles, we have the standard model of elementary particles. This is like a periodic table of the 30 known fundamental elements, the basic of the very basic particles making up all matter. See gluon over here? Quantum chromodynamics is the quantum field theory of this extraordinary particle mapping out its behavior.
For starters, imagine a proton.
It has the diameter of about quadrillionth of a meter. Inside these are loads of quark and antiquark pairs zooming at the speed of light, forming new quarks and antiquarks as well as annihilating the same. However, at any one time, a proton would be having 3 valence quarks, up, up, and down. And they may never be the exact same ones at all times.
With all that crazy stuff happening in that insanely tiny space, a ridiculously ultra mega force needs to be there to hold them all together.
This is the strong force, which happens to be the strongest of the 4 fundamental forces of nature. And the particle carrying the strong force is, you guessed it, gluon. The gluon is a massless particle exchanged between quarks. Under quantum chromodynamics, gluons interact with both quarks and other gluons.
Okay, so if gluon is the protagonist, why is it called quantum chromodynamics and not something like quantum gluodynamics?
When we talk about any force, a few things come up rather intrinsically. For example, for the electromagnetic force, the intrinsic property is its charge. Similarly, for the strong force, its charge is a property called color, namely red, blue, and green.
But why red, blue, and green and not something like orange, yellow, and pink?
Since when talking about proton, or any baryon for that matter, we like to think in terms of the 3 valence quarks. Each of the 3 has a different color, charge, at any given time. The color is a tricky property, intentionally given red, blue, and green charges to be made analogous to the shining of red, blue, and green lights turning to white light. And hence quarks have the color property but baryons don't. Since the Greek for color is chroma, there you have it, quantum chromodynamics.